Welcome back. In this video, we're going to talk about line integrals, briefly discuss what they mean, look at the formula for how to integrate them, and then just really spend a lot of time working through a bunch of examples, going through a lot of the mechanics on it because I know it can be kind of tricky. So anyway, let's go ahead and jump in. So line integrals, it's actually really exactly what the name would suggest. You're doing an integral, but you're doing it over you're restricted to a line instead of like a region. You know how in previous videos we did integrals over volumes and areas, but now we're just saying, okay, we're in like multi-dimensional space and we really just want to see what happens on a particular line instead of volume or area. And the way that that's written is we have an integral that's restricted to a line C, or a curve C, I shouldn't say line, I guess, of a function f, and then ds. Okay, and that ds kind of has the same meaning as like dA or dV. It's just a little piece of the line segment. And to actually be able to integrate this, I mean, looking at it, it's somewhat uninformative, but what we can do is kind of appeal to the same ideas that we applied when we were working with parameterized, vectorized type functions and say, okay, I can take this curve here and parameterize it. And then once I have a parameterization for it, I could plug it into f. So we have the integral over f of the parameterization r of t. So this is the line just parameterized in terms of t. And then t has to have some bounds, a and b. And that gives us the nice, what we can integrate over, applying the fundamental theorem of calculus and all that stuff. But because we changed what we plug into f here, we have to kind of compensate for that by multiplying by the length of our derivative of our parameterized version of the line. And this is just kind of the same idea of, you know, change of variables, u sub, that whole deal, kind of up there, maybe along the lines of adding that extra r in when we do the cylindrical coordinates integration. But very important, don't forget that. So yeah, so we wind up with this parameterization of the line for r of t. We plug that into f, and then we integrate with that instead because it's much, much easier than trying to figure out what exactly that means. So where r of t is the parameterization of the curve C on an interval a to b. Okay, so let's go ahead and just jump in with some examples and start looking at really just what it looks like to break a problem down like this. So for our first example, we are going to find the integral over a curve C of f ds when our function f of xy is equal to x plus y squared, and our curve C is the line line segment from the point -5, -3 to 0, 2. Okay, great. All right, so remember that the main goal here is to take our integral over C of f ds and rewrite this as an integral from a to b of f evaluated on some parameterized version of our line. And plugging this parameterized version of the line kind of has the same effect as restricting f to that line. And then times the derivative r of t dt. So we have to really just basically construct this guy right here. Well, how do we do that? Step one, we need to parameterize the curve that we're looking at. And this actually uses the exact same strategies that we used many, many weeks ago when we talked about, well, parameterized vector versions of functions. So if you're kind of uncertain about how exactly this works, I'll do a little bit of review in this video, but not too terribly much. I strongly recommend that you go back and take a look at that video from earlier if you're have any in-depth questions about how this works. But in this particular instance, we're looking at a line segment between 2 points. And if we kind of remember back to that, we know that a line segment has a parameterization r of t equal to a base point p plus t times some vector v. So we really just have to pick a base point. I'll call it, I don't know, 0, 2 can be our base point here. And actually, I take it back. Let's call this one our base point. And then from there, we just figure out what the rest of this is. So our base point P is equal to -5, -3. And then our vector V is just equal to the difference between those 2 points. So we'll have 0, 2, -5, and then 2 minus 3, or 2 minus -3, which is 5 as well. So filling this in, my parameterization becomes -5, -3, plus T times this vector here, which I can rewrite as -5 plus 5t, and then -3 plus 5t as well. Okay, great. Now at this point, oh, and one thing that I forgot to mention that we kind of really didn't talk about maybe previously, but when we're just looking to go between this point and this point, like we really don't care about the rest of the line. We only care about the area between those two. We know that T has to be between 0 and 1, because when T is equal to 0, well, we start at our base point because this piece goes away. And then when T is equal to 1, we add the full vector there and you wind up at your final point 0, 2. So in this case, when we're parameterizing line segments, it's always between 0 and 1. Okay, so now that I've got this parameterization, the other piece that I need here is the norm of that derivative there. So I need to take the derivative of my parameterized line segment, and that's going to be 5, 5, which means then that the length of that is equal to, well, it'll be root 50. Okay, great. So now at this point, what I want to try to do is write f in terms of the coordinates of r of t. And I'm going to actually need a new page for this. Okay, because remember that the goal is we have to get f evaluated at r of t. So we had said that r of t was equal to the vector -5 plus 5t and -3 plus 5t. So this means, looking at these two coordinates right here, x has to be equal to -5 plus 5t, and y has to be equal to -3 plus 5t. So to be able to swap this out for f, so our original f of xy was equal to x plus y squared. This now means that f of r of t is equal to, I just put this in for x, -5 plus 5t plus -3 plus 5t, oops, squared, like so. And you can FOIL that out, simplify it down, all that good stuff, and you get 4 plus 25t plus 25t squared. And the reason that I do this is because I know that I'm going to plug that into an integral, which brings us to step 3. We just plug all of this information that we had found back into the integral. We remember that the original goal was to write this integral here as an integral from a to b, f evaluated at r of t, times the length of r prime of t dt. So this is equal to, we said, a and b are going to be our bounds on t, which are 0 and 1. Oh. Before I jump into all of that, let's go back and restate. So we're going to plug into our integral, and our bounds are the bounds we found on t. So The integral that we have is integral from 0 to 1, because those were our bounds on t. Sorry, I had to rewind there for a second. And then we found that f evaluated to r prime of t is this guy right here. And then this piece right here, that norm was equal to root 50. And then we have dt. And now you can integrate as normal to complete the problem. And that's pretty much all there is to it. So I'll leave that piece to you, the integration part, but that really isn't too bad. It's just a polynomial scaled by root 50. So quite a bit nicer to work with than this original setup for sure. All right. Let's look at another example. In this one, we are going to take the integral of a curve, or over a curve C of x squared plus y squared plus z ds, where our curve is the part of the helix given by r of t equal to cosine of 2t, sine of 2t, t, where t is greater than 0, but less than or equal to 4 pi. Okay. So let's kind of like recall our original breakdown here. Step 1 was to parameterize the curve, but it's already parameterized. Because we've already been given everything in terms of t, and bounds on t were also given to us. So we just need to find our r prime of t. And this is going to be equal to -2 cosine of 2t, 2 sine, oops, nope, not cosine, that'll be a sine, 2 cosine of 2t, and then a 1. So then the length of this winds up being equal to root 5. Okay. Step 2. We are going to write f in terms of the coordinates of c, or c, t, r of t. And based on these coordinates up here, x is equal to cosine of 2t, y is equal to sine of 2t, and z is just equal to t. So our original function of f, x, y, z equal to x squared plus y squared plus z is now going to become cosine squared 2t plus sine squared 2t, and then plus t. Which this actually simplifies down really nicely because we have 2 cosine squareds in there, and that's just going to become 1 plus t. So that's pretty great. Now, step 3, remember that we want to plug. Our goal had been to take the integral over c of f ds and write it as an integral from a to b of f of r of t times the length of r prime of t. We need to plug pieces in. So in this case, we are going to get the integral from this time 0 to 4 pi. And then this guy right here becomes the 1 plus t. And then this piece right here is just going to be the root 5 dt. And now again, at this point, you just integrate as normal. And that's pretty much it. Yep. So again, main idea here is that, and I guess I probably should have written this back up here at the top, was to be able to set it up like that, go through, find all your pieces, plug it in at the end, integrate using standard strategies. Cool. Next example, I want to do kind of like a multi-part one here. So now we're going to integrate over curve C, the function 3x plus 2y plus z ds, where C is the piecewise linear path with vertices at 0, 0, 0, 1, 1, 1, and 2, 3, 4. Okay. So again, as always, our main goal is to take the integral over our curve C of our function f and write it as an easier integral to integrate over AB or from A to B of f evaluated at some parameterized version of our curve times the length of the derivative of that curve dt. Okay. But this one's going to actually be a little bit trickier to do than the last two, because what we can think of as C right here, it's got 3 line segments to it. This is kind of tracing out a triangle, okay? So C has 3 line segments, which means there are 3 different rules we have to follow for each one. And these 3 line segments are made by, I guess I should label my points, P, Q, and R. So my first line segment is PQ. My second line segment is going from Q to R. And then my third line segment is going from R to P. And this creates 3 different rules, or 3 different line segments. I can call this one C1, this one C2, and this one C3. And so since I have 3 different rules, I have to integrate in 3 different parts, or to break my integral into 3 different parts. So we have the integral over all of C, f ds, is equal to the integral over C1 of f ds, plus the integral over C2 of f ds, plus our integral over C3 f ds. So the main idea here is just that we can take our curve and break it up into 3 different segments if we need to, add them all back together, and we get our final answer. So we have to apply the idea of the integral over the curve f ds is equal to the integral from A to B of f at r of t times the length of r prime of t dt on each curve. Okay. So first we have to parameterize them all. So C1 is equal to R of t, which is going to be the line segments. That one goes from 0, 0 to 1, 1, 1. So what you get then for that one will be 0, 0, 0 plus t 1, 1, 1. So this is just the vector t, t, t. So for that one, you get that r prime of t is just equal to, well, 1, 1, 1, which means that the length of that vector, or of that derivative, is just equal to root 3. And we also note that this implies that x is equal to t, y is equal to t in this case, and z is equal to t in this case. So, yeah. Okay, so now let's parameterize C2. This is going to be the line segment, let's not call it R, let's call it S. S of t equal to 1, 1, 1 plus t times 1, 2, 3. So that's equal to 1 plus 2t, 1 plus, 1 plus t, 1 plus 2t, and then 1 plus 3t. So then S prime of t is equal to 1, 2, 3. So the length of that is equal to root 14. And again, we note that x also has to be equal to 1 plus t, y has to be equal to 1 plus 2t, and z has to be equal to 1 plus 3t. for this curve right here. And now for the case of C3, we'll call this one Q, little q. This is equal to the parameterized line segment 2, 3, 4 plus t times -2, -3, -4. And so that gives me 2, -2t, 3 minus 3t, and then 4 minus 4t. So q prime of t is equal to, well, -2, -3, and -4. And so the length of that is equal to √29. And then finally, just so we can convert things over later, x has to be equal to the x component there. Y is equal to 3 minus 3t, and z is equal to 4 minus 4t. All right. Oh, and one thing that I forgot to mention is that, as I said earlier, whenever we are parameterizing a line segment, t is going between 0 and 1. So it's going between 0 and 1 in all of these. All right, so that's going to give us our bounds on t for each integral. All right, let's set them all up individually using the information that we found. Okay, so we had our integral over C1 of 3x plus 2y plus z, and then this is little ds. And rearranging this, we set our bounds for t were between 0 and 1. Going back to this page right here, we see that x was equal to t. So I have 3t plus 2t plus t. And then this is times √3 dt. Okay, so integrating that, what you get at the end will be 3 √3. All right, let's do the next one. So second curve, same function. Integral from 0 to 1, and now I got to start swapping out my x, y, and z, and that's going to be based off of these identities right here from the coordinates that we pulled from our parameterized curve. So 3 times 1 plus t plus 2 times 1 plus 2t plus 1 plus 3t. Oops, and all of that is multiplied by √14, and then we have a dt. Integrating that with respect to t, and your final answer that you get for that piece right there is 11 times √14. And then we have our final line segment to work with. 3x plus 2y plus z ds equals integral from 0 to 1 of, all right, now we got to start swapping some pieces out. Looking at our parameterizations here, we're going to get that x is equal to 2 minus 2t. And then y is equal to 3 minus 3t. And then z was equal to 4 minus 4t. This is times √29. And then we still have the dt. There we go. Okay, so integrating that with respect to t, you're going to get 8 √29. So now this is for each of these individual line segments. Our original integral was over all of that line segment C, which was all those pieces added together. So our final answer is each of these pieces added up. And don't forget to do that at the end of these kinds of problems. All right. Okay. That's pretty much it for that example right there. Let's do one that takes like a little bit of a different parameterization on it. In this one, we're going to do a curve. We're integrating the function x times cosine of y ds, where our curve is part of a function. It's going to be given by a piece of the graph from y equal x cubed for x being between -1 and 4. Okay, so let's talk a little bit about what parameterizing these guys looks like. So when parameterizing a piece of a graph, when you have y equal to some function of x, which I'll denote with an h of x, we let x be equal to t, and y is equal to h of t, which really maybe seems quite silly. What you're going to get for your parameterization is r of t equals t h of t. Okay, so maybe that looks a little bit vague. Oh, and the bounds of t are the same as the bounds on x. Which is something you want to be careful about because sometimes you're given bounds on y instead and you have to make the appropriate adjustments. Okay, so just to make this a little bit more concrete, in our case, what this means is that since y is equal to x cubed, if we were to take x equal to t, we get that y is equal to t cubed, and t, since the bounds of t are the same as the bounds on x, t is going to be between -1 and 4, just like so. So now r of t is equal to t cubed, and r prime of t is equal to 1 3t squared. So then the length of r prime of t is equal to root 1 plus 9t cubed, or to the 4th. Oops, sorry. Yeah. Okay, so to be able to actually set this up, we have to notice that this right here, this is our x. That right there was our y. So our integral over a curve c of x cosine of y ds is now going to become the integral from -1 to 4, because those are our bounds on t. And then t goes in for x. We get cosine of t cubed. And then we multiply by the length of r prime of t here. And we get 1 plus 9t to the 4th dt. Okay. So for this particular instance right here, you look at this and you're like, oh my gosh, I don't know how to integrate that. I don't know how to integrate that either. This is the point where you go back and you check the instructions on your homework problem and you say, you notice, oh, I was told not to evaluate that. So anytime you wind up with something that's super messy like this, do not evaluate it until you have double checked your homework assignment. In this particular instance, a lot of times you will find that you are specifically told not to integrate that particular setup. So just something to keep in mind, because this is particularly nasty. Okay. So that's pretty much it for that example. Let's do one more. So for this one, we're integrating over a curve C, y sine of x ds, where C is a piece of the graph y is equal to e to the x, where 1 is less than or equal to y less than or equal to e to the x. Okay, so remember that our goal is to take this format here and rewrite it as an integral from a to b of f evaluated at r of t times r prime of t dt, or norm of r prime of t. So first we have to parameterize our function here, or our curve, not our function, our curve. And in this particular instance, we're taking t equal to x because we have a function. And then that means that y is going to become e raised to the t. Okay, so my r of t is equal to t e raised to the t, and r prime of t is equal to 1 e to the t, and the length of that is equal to root 1 plus e to the 2t. Okay. However, I am missing my bounds on t, and if I look at what I was given here, my bounds are given in terms of y and not in terms of x, so I've got to be able to deduce those. So we need bounds for t, and we will determine them from the y bounds. So we note that 1 is less than or equal to y, less than or equal to e to the t, and or not e to the t, e to the 3. But y is equal to e to the t, so I can swap that out. And well, if I just look at this half right here and I say, okay, I want 1 here. In order to get a 1 on this bound, t would have to be equal to 0. And in order to get e to the 3 up here, that exponent 3, well, it'd have to match that exponent t. So t has to be between 0 and 3. So to set this up, this is going to be equal to the integral from 0 to 3. Oh, and I need my conversion from y and x into t. So, oh wait, no, we already wrote this down up here. So I've got e to the t sine of t, and then times the square root of 1 plus e to the 2t dt. All right, and that's pretty much all there is to that example right there. Great. Okay, so I do actually have a few more examples, but this video is already really quite long, so I'm going to go ahead and split that off into a separate chunk. So I'll go ahead and quit here, but in my next example, or my next video, I'll talk about some examples working with an ellipse, a circle, and then one that's a little bit more unusual, working with just breaking it down into a lot of different pieces. So I'll see you guys then.